Good morning, everyone. Thank you for joining our lecture again. Had a great pleasure yesterday talking to several of our folks during the office hour, answered quite a bit of question regarding the homework and regarding the exams. If you still need to go over your exam with me, please just drop me an email and we can schedule a time to do that. Other than that, I have some questions about the quiz number 5, which I want to go over quickly, and then we'll get into shear today. Okay. So with that, I want to make inquiry. Any questions on the exam, the homework, and quizzes? Anything, folks?
I have a question.
Yes, sir. Oh, yes.
For the homework, I know you explained that you're not allowed to tell us the answers, but if we're not sure about certain steps, are we allowed to email you and just say, can you just let us know like wrong equations or wrong steps? Or what information can you give us from if we send you the homework before the due date?
Oh, sure. Thanks. That's a good question. First of all, I'm working with the TA to come up with a posting strategy. But if we were to post it online, we'll probably just post the final number. And regarding to the detailed process, I'm still not sure we're going to post that. And explain the reason twice already. I just want to quickly explain again. Is that because we worry about people use it as a template. And that's what I seen in the exam, that people just use the homework as a template without thinking too much. So that may be very helpful to few of us, but maybe not so for majority of us. So that's the reason. Now coming back on the information, the homework, pretty much if you send me an email asking how how we do the homework, I answer the questions and provide the feedback. But I really don't like to do this. Is my approach correct? Type of answer. You can ask me specifics. For example, should I do this? Should I do that? Does this make sense? And if you feel like you're not getting enough information, you can always come to office hour 2 o'clock p.m. Every Tuesday. Now, if you have conflict at that time, you can just email me and we can set up individual time. And now I have talked to like 4 or 5 of us separately, individually about their homeworks, and I believe they got some help. So, in your case, if you just need a special help on your particular homework, you can just drop by email. We can Zoom chat anytime, based on the conveniences. But that's all. Does that answer the question?
Yes, thank you.
Yeah, not a problem. Like I said, you will find it very approachable me as a instructor. So whenever you have a question, you email me or you're trying to schedule a talk with me, I think I'm always available and I can make myself available to answer questions. So just drop my email to me, okay? All right. Any other questions about the homework and exam and the quizzes, anything? All right. Okay, so let me quickly get back to the main topic. And I just want to quickly go over about this quiz 5. I got like 2 emails asking me some questions about it. So let me share my screen. Okay. All right, so if you guys see my screen, I'm working on the iPad right now. And the problem I got asked is how to solve quiz 5, essentially, right? So if you look at the quiz 5, we already, sorry, I think my screen is paused. Let me do this again, reshare. Okay. All right, so for the quiz 5, we already got a geometry, right? So that is the T-beam geometry, okay? And then for the T-beam, we already talked about this. There are 2 scenarios. Sorry, excuse me. There are 2 scenarios. One is that we can treat it as the wing and the web, and this is called scenario 2. Okay. Now the other one, now the reason why I put it in letter because I don't think you see this one, but even if you do, the compressive zone will be kept within the flange, and that's called scenario 1. Right? So if you look at the quiz 5 particularly, it gave you the reinforcement area, which we calculated to be around 20 inch squared. And that's quite a bit. All right. So what we did is that I said in the quiz that you don't have to worry about how to fit a bar in for now. You can simply assume you just have a lump of steel right here, AS. Okay. And let it to be 20 inch squared. All right. So that's what you do. You put a lump of steel there, and you can assume the height, right, by doing h equal to ds plus, now either you can do 3.5 or 2.5. At this point, it doesn't really matter to me, but I prefer you do 3.5, okay, because you have a lot of bars there, but that's okay still. Once you get the depth, the first thing you do is to figure out which scenario. Now, we cut this number because we assume scenario 1. All right, so let's go with scenario 2 first. So if we go to scenario 2, the first thing is to separate the reinforcement. Okay, so we're back to how to calculate the moment capacity for T-beam, basically, right? So what you do is that we said that assume is scenario 2, right? So you have ASF, that is the reinforcement in the flange, corresponding to the flange, and that equal to Fy, and you let it, so this is flange, and you let it equal to the compressive part, which is 0.85 prime C, and now the width is BF, assume this is BF, and this is BW, minus BW, to get you the wing or the flange width, okay, and then multiply by the flange height, which is HF or H. In this case, let's say HF because I already use H as my total height.
Hey, Professor.
All right. Yes, ma'am.
For your scenario 2 on the right-hand side, isn't that supposed to be scenario 1?
I'm sorry. Can you say it again?
Okay, so for your scenario 2 on the right-hand side, is that supposed to be scenario 1?
Yeah, this is scenario 1,
Okay.
right? So that's like the compressive zone is within the flange.
Okay. To me, it just looked like a 2. Sorry.
Oh, so sorry about that. How about that? Okay, sorry about that. Okay, yeah, that's scenario 1. Okay, 2 is on the left. All right, so let's get back to this. So this is how we define the reinforcement for flange, right? So we can immediately calculate the flange, right? So it's basically this bunch. So I'm just gonna save time here because I have other things to talk about today, but this is how we get determine the reinforcement for the flange, right? Now, separately, we can define the web reinforcement. So this is SW, and then you write equation first, of course, and this is 0.85 F prime C. And now be careful, this is A, B, W. All right, and where is A? A is right here. Okay, so now with this, you could get ASW. But be careful, there's a problem. What is the problem? That is, you don't know A. Don't know A, right? But you do know ASW in this case. What is ASW? That equal to the provided steel AS, right? Minus the ASF. Okay, so in the web, now the story changes because now we can compute A, which is ASW Fy divided by 0.85 F prime C BW. Okay, all right, so now this is essentially, you can think of it as more like a rectangular section now, but only difference is that this is called BW and this is ASW, right? And now you're getting the compressive zone A here, and essentially you can just compute the moment, right? So now I have this flange and I have this. So I calculate the moment capacity separately, all right? So I can carry on like this, or I can probably shift this down here. So finish the top part first. For you, it probably doesn't make a difference, but just for me, it's easier to see it. So if you got this ASF already here, you know that for the flange, the tension equal to ASF and Fy, and the moment, nominal moment resistance or nominal flexure strength contributed from the flange equal to ASF Fy, and that is the tension side of it. So I want to do a little bit drawing here, so be careful. Now you only have the flange that take care of the compression. So the distance, when you sum the moment, right? This part should be HF divided by 2, half of it. And that is where the compression center is at. So the distance between the compressive center to the depths, right? That is the JD leaving arm for this one, JDF for the flange. So now you remember this is ds. Okay, so the distance should be ds minus HF divided by 2. Okay, so that's how you calculate the moment contribution by the flange, right? So for the web, you already have A, right? So what you do is Mn for the web equal to ASWFY, which is the tension, right, from the web, and multiplied by the distance. And now this distance here from the drawing here, this is ds, right? So ds minus the center of the compression force, right? And that is A divided by 2, so half A. Okay, so now that is the moment contributed by the web. So ideally at this point, you can do Mn equal to MnF plus MnW, W to find out the total moment resistance. But we might run into a problem is that after you've done this, what about phi, stress reduction factor? And even more importantly, whether the stress in the steel yielded or not. So these are the two questions we need to answer. So how to answer these two questions? We have to go back to the web, okay, not the flange, but the web. So how to do that, right? So if I want to call this step 1, and this is step 2, and step 3 would be, you take a look at the strain diagram, right? Take a look at the strain diagram. This is epsilon Cu equal to 0.003, all right? And here I have epsilon s, which I don't know, but I have the depth of it, so ds. Then again, you can make assumption here for ds. Like I said, we use h minus 3.5 inches, which is fine. You can use 2.5, which is okay for the quiz, is okay. All right. So this is the strain diagram. All right. So now we need to see, which is actual compressive zone. So although you got to think the C is in the web, but this equation C equal to A divided by beta 1 still valid. C equal to A divided by beta 1 still valid. So once you have C, I want to find the strain in the steel. So epsilon S equal to here ds minus C divided by C multiplied by epsilon Cu. And this is 0.003. By the way, you can get epsilon S. Once you get epsilon S, right? So epsilon S, you compare it to epsilon Y. In this case, of 60 KSI, 0.00207. So make sure it's yielded. Okay, and then you can make another assumption, say assume, since we don't know the exactly bar configuration, assume epsilon s equal to epsilon t, okay? And by doing that, you can also judge whether epsilon s is smaller than 0.005, tension controlled or not, or transition, right? And use that equation for phi, and remember, this is phi, this is 0.002, 0.005, and 0.02 here is 0.65, and 0.5 here, 0.9 in between linear interpolation, right? And then you can find phi. And now you can get phi Mn. Okay, so I realize that this is basically an analysis based on what we talked about last lecture in design, but it's essentially the same thing. Okay, so at this point, if you arrive here, you should know that in the process where you get A, you can do a quick check whether A is falling within the flange or not. All right, so if your A is not falling in the flange, that means the first estimation of reinforcement here maybe is too much. We probably need to reduce that. But in our case, you should find that A is bigger than HF in this quiz.
Professor, where do you find a 20?
This is not fine. I believe in our last lecture, we just gave this number for the quiz 5 for you guys to run.
It was 8, number 9 bars.
Is it? So sorry about
Yes.
that. Can I make a correction here? Yeah, thanks. Sorry about that. Somewhere I get 20, maybe it's the height.
It was a DS. You put, it might need to be adjusted. That's what you put.
I'm sorry.
DS was you put 20 inches and then you put a note saying it might need to be adjusted. What do you mean
Yeah.
by that?
So here you can see that when I don't know DS, I use H and I can estimate my DS, right?
Oh,
But
okay.
if I say DS equal to 20 inch, and you can just use this number. When I say you can adjust it, is that I see some students trying to fit 8, 9 bars in the section, right? And when they try to fit in, this is not 20 inches anymore, apparently, because it's a very narrow fit. So you may end up with 17.5, 18 inches. What I'm trying to say is you can go ahead with whatever number you come up with. I'm pretty sure you can still gonna come to this conclusion that it's still scenario number 2, and you can follow the process, get you the final moment capacity.
Oh, okay. Thank you.
Yeah, no problem. I just want you guys to continue with whatever height you determine at first, because the shorter height you end up with, right? You just have to stretch your steel further, because you have get this thing, right? You have smaller compressive zone, right? So you have larger strain in the steel to make sure you yield it and all. That's the only difference. Okay. All right. Any other question for quiz 5? Let me see if I can pick up this question from chat.
So we
Oh,
can just
Larry.
treat it as a big chunk of steel instead of just fitting the 8 bars, or we just have to fit the 8 bars.
Either way is fine. The aim of this quiz is I want you to run a forward analysis. Say design is more like a reverse way, right? You don't know and you make a guess and a reinforcement. But I want you to exercise a forward analysis, basically showing the reinforcement and then find out the moment capacity. So the detail and the bar detailing, that's not the concern for this quiz here.
Okay, thank you.
Yeah, not a problem. So chapter in the book we are currently in, we are currently in shear, so that's supposed to be chapter 6, and I can double check on that. And we are talking about here T-beam. This is still flexure, okay? And for flexure, you should find them in chapter 4 in a textbook, okay? All right, any other questions about this quiz? Any other question about this T-beam? All right, let me say this. In the exam, we're not going to test you on the T-beam design. We're mainly gonna, if we were to test you, we're probably just gonna test you on the analysis. Okay, so for the analysis part, there's also irregular section. You know, we talk about this kind of like this with opening or this with opening. These are both in chapter 4, I believe. So between T-beam and irregular section, we pick one for a regular problem, like a full workout problem. In problem 1, it's going to be multiple choice and filling in the blank. There, we'll only test you the T-beam analysis. It's going to be basic stuff, basically asking to check if it's scenario 1, scenario 2, if the compressive zone that is within the flange or not within the flange, that kind of quick things. Okay, so I'm more worried about the irregular section for the exam number 2, that is. All right. Okay. Any other question on this? All right. So if not, I'm going to extend the quiz 5. I will extend the deadline. Let me write down here because some students say they cannot listen clearly. So extend the deadline for quiz 5 for 2 next Monday. All right. So you have more time to go over it and email me if you run into a trouble and I can help guide you through it. But don't email me and say, look, this is my number. You think this number is right or wrong? I cannot do that. Okay. But if you just say, hey, I got it stuck here, I don't know. Like one lady yesterday emailed me, and I just tell her I'm going to go over it today. So something like that, I will definitely do. Okay. So quiz 5 will be extended to Monday and 8th, so you have more time to go over it. Okay. All right. Any questions on this, on the T-beam? Anything else, folks? All right, okay. So this is that last piece of the T-beam. I just want to clarify that, but let's quickly dive in lecture 12, okay? And we're going to talk about shear, continue to talk about design for shear, all right? Okay, and one more thing I forgot to mention is that we will have a lab, more like a design lab in this course as we're on schedule, but we'll talk about that tomorrow on Thursday lab session, okay? So let's quickly get back on the design for shear here, is that today we're going to talk about objective is understand the shear mechanism. So shear transfer mechanism. Okay, shear transfer mechanism. So what is shear transfer, right? That means the forces, the shear force being transferred from one segment of the beam to the other segment of the beam. Okay, now if you remember last time we showed the stress distribution of a beam, and that is elastic uncracked beam, right? And we showed you that essentially the crack is going to run diagonal direction like this. Okay, and just crack through the beam like that. Okay, and we also provided the reinforcement, right? Say this blue color, so transverse reinforcement go here, and longitudinal reinforcement go here to provide a resistance for the cracked section. Okay, so when I look at the crack, when I look at this red crack, right, I want to take a look at the free body diagram, or how the force was transferred from one segment to the other segment. And this is what I see. Okay, this is what I see. So I have end of the column, and I have support. And remember, I have two-way support here on the left. And now I have a literally vertical small section here, vertical small section here. Okay, and that is the residue due to the cracking, residue due to the cracking. Okay, and now I have the crack and goes more like this, a 45-degree, but not so exactly, but like a curve, and then end up like that. So that's the crack look like, right? So naturally, let me split this part away from it, expose the right-hand side of it. Okay, expose the right-hand side, and that's the right-hand side of the piece of the concrete. All right, and let's examine, let me just zoom in here. Let's examine the forces that exposed by doing this cut. Okay, now first of all, I expose this vertical section, and let's call it compression C1. Okay, so that's the remaining compression from the top part. And then I will have a shear force, and I call it VCY. Okay, shear force VCY. All right, now on the diagonal crack, I have the shear force, I call it VA. Okay, and then I have the corresponding counterpart, also VA, on the bottom part to balance it. All right, and then I have shear force VD, and that is caused by the Dowling effect. That means by the longitudinal bars, right? So think of it, the bars is just gonna push the concrete, right, to resist the concrete being shear apart. So the shear on the transverse section of the bars provided that VD, the Dowell shear force. Okay, and naturally, since it's balanced, so I have the VD on the left-hand side as well, and then I have tension. Okay, and sorry about that. I should actually cut it, right? Because it's being cut here, it's being cut here. I should have tension as well, and this tension is called T2. And of course, left-hand side, same magnitude but opposite direction. Okay, T2. So these are all the forces. These are all the forces you see on the section, actually near the crack, right, near the crack. And let me just push this a little bit over, and let me explain, right? So now from this, these are all the forces on the crack, Okay, so we can say that the shear stress or shear forces in this way, shear stress, okay, can be transferred across the diagonal crack. So across the diagonal crack. Okay, cross the diagonal crack through two main contributions. So the compression is definitely not it. So the shear force, right? Only pick up the shear, the VCY, that is shear on the top remaining compressive zone, and VD, which is shear from the bottom longitudinal bar, and VA, which is shear on the diagonal crack location, right? So now these are the three major shear contributions we see, right? So we just see VCY, and that is shear in the uncracked, uncracked compressive zone. Okay, in the uncracked compressive zone. So that's the first contribution. All right. Second shear contribution, and wise one said this will show up in the exam, right? So pay attention, right? VA, that is a shear on the diagonal crack. Okay, and we give it name, said interface. Interface. Okay, shear transfer. And notice that I have a A here. What does A represent, stand for, right? It basically stands for aggregate interlock. Okay, aggregate interlock. Now you may say, Bob, what is aggregate interlock? I cannot see it. So let me put a magnifying glass here on the interface just to show you what it looks like, right? So what it looks like is that I will have a zoom in a picture of the crack. So it's definitely not flat anymore. It's definitely not flat anymore. It's more like a zigzag. It's more like a zigzag, right? And if you pay attention to it, these zigzags are basically aggregates, rocks, coarse aggregates inside the concrete, right? So these aggregates will rub against, use a different color here, rub against the aggregates from a bottom diagonal crack side, okay, from bottom diagonal crack side, and to give you that shear resistance or shear transfer, like we labeled VA. Okay, so this is what means by aggregate interlocking. Okay, so this is aggregate. Well, I already put it here, so let me just link it to this one. Aggregate interlock. Okay, so that's the contribution by the diagonal crack. And then last but not least, talk about the three contribution. I realize that when I skip a page, just go to the next page, but make sure in your notes they're together, three together. So VD is called a dowel action. Dowel action of the longitudinal reinforcement. Spell errors. Longitudinal reinforcement. Okay, that's the dowel reaction. So with this three, now I can say my total shear, and this is shear contributed by concrete alone. Okay, only. Total shear contribution from the concrete only. Okay, that consists of VA, which is a shear interlock, right? Aggregate interlock, plus VCY, which is the compressive zone, right? Shear residue, and then VD, which is the dowel action from the longitudinal reinforcement. Okay, so these are the total shear resistance from the concrete that you can get. Okay, now this is all fine, right? This is all fine. And when design, we want to make sure that VU, when design, right? When design, we want to make sure that VU has to be smaller or equal than phi VC. Again, this is stress reduction factor. You've seen this again. And for our case, for shear, okay, and this is very, very important, and don't get it wrong. And this number equal to 0.75 by default. Remember from ACI 318 code, this is default, by default, 0.75, okay? And VC, of course, is the concrete contribution, all right? So when this happens, right, we are, we feel safe, we're okay. I wouldn't write down okay because we still had to put a steel in it, but that's not an issue here right now, okay? So this is what we wanted to see, all right? But what if What if the design is, or the concrete contribution is not sufficient? What if just the concrete alone cannot take it, right? So in this case, we call it web reinforcement or transverse reinforcement or stirrups, several names, right? So the web reinforcement is needed. You need steel, basically, right? Need steel. All right, so you need steel. So how do we put steel in, right? How do we put the steel in? And again, we have to go back to the drawing here, right? How to put the steel in. So let me show you, right? So this is the crack. Again, has this nice curve and draw like that. Okay, so you notice that when I draw the crack, right, there's one is the vertical compressive zone, and this is arc-like diagonal crack, and this is another fracture crack remaining portion of it, right? It's a straight again, right, to put your bars in. All right, just some minor details. And then I have made this piece right here to worry about. Okay, and we showed you already, right? This is the constraint, and now I have Vy, VCy, and we have compression C1, we have VA, VA, and we have VD, and we have VD here. And again, we have tension T2 and tension T2, right? So that was exposed, that was exposed. Okay, so to resist the shear, okay, to resist the shear, and you can erase or you can leave them there, but let me just do this to show better. So to resist shear, I'm gonna remove the tension and compression from it. Essentially just VCy, VA, and VD to care about, right? So if I want to resist the shear, what I'm going to do is I'm gonna build cages. I'm going to build cages. So on top of the longitudinal reinforcement, I always have to have for a beam for flexure, I need to provide stirrups. All right, and to hang the stirrups to it, right? So as you can see, for regular stirrup cages, right, on the construction site, these are more like stirrups. I'm trying to draw a 3D view for you, okay? Of course, they're not like hard cornered. They're more like a round cornered, okay? So even better, let me just draw it completely like what we did before. So we have this kind of like a burn bent, and I have another bent like so. And they are, this should be parallel, okay? And then I run my longitudinal reinforcement like so, okay? So I have another stirrups sticking up like that, curve like this, and another stirrups sticking out like that, curve like this, curve like this. Okay, so these are the longitudinal reinforcement at the bottom. Oops. Okay, longitudinal reinforcement at the bottom here. Okay, and then these are the web reinforcement or transverse reinforcement or stirrups. Okay, why we call them web reinforcement? Because they stay in the middle, okay? Now, you notice to build this cage, I need another bar to run through the hoops, right? Run through the hoops. Okay, so these are called the compressive reinforcement, remember? Okay, and in construction side, we usually call them hanger bars. Why? Because they're utilized for hanging the stirrups on them, okay? Hanging the stirrups on them. So if I build this cage, right, and this is 3D view of reinforcement cage, okay? And from the side view, I don't see this complication, right? All I see is the top reinforcement is in compression, bottom in tension, and I have stirrups here, like a leg, the stirrups here, like a leg, and then stirrups here, crossing the crack, stirrups here. Okay, so essentially we're looking at the side view, right? Side view. That means we're looking at the side like this. Side view. Okay, but be careful. Each leg you see in here, right? Each blue line you see in here, right? This essentially is cutting across. Well, let me clear up the number. So this is 1, 2, 3, 4, 1, 2, 3, 4. So it must be this one. So this fellow here that we exposed, right? It has to cut through one leg, two legs. All right. So from the side view, these stirrups provide additional shear resistance through these two legs here, through the cross section of these two legs here. So now this is the reinforcement provided shear resistance, Vs, and together Vs, Vs, Vs. Okay, and that is the steel. That is the steel. All right, so just got to be careful, right? If I call this Vs, the corresponding cross-section area for shear, I call this ASV to differentiate from AS as a flexure. All right, now there's some details, right? We need to clarify. Now for ASV, right? It really depends on number of legs in the stirrups. Okay, how so? For example, if I have this stirrups, right? If I have this stirrups, I have one cut and two cut. So ASV is the area of two legs. This is one leg, this is two leg, right? If I have this kind of reinforcement, okay, and actually I should draw it like this, but that's fine. So I have two stirrups overlapped, right? Now I have 1, 2, 3, 4. 1, 2, right? So now ASV equal to area of 4 legs. Okay, there are some subtle details. So be careful what kind of area you have here. All right, so that is the steel or web reinforcement inside the beam in the cage, right, to resist the additional shear. So with this, we'll say that the total shear contribution should equal to the contribution of concrete plus the contribution of steel. All right, and for all our purpose that we know that the contribution of concrete to resist shear come from three parts: the aggregate interlocking, compressive zone shear, and the dowel action. But don't really worry about it because it's all lumped in. All lumped into VC. All right, so now that is the concept for the shear reinforcement. Okay, so I just want to quickly pause here. Any questions on this conceptual drawings and illustrations? Anything? Anything?
Can you scroll back down to the bottom?
Yep. Can you see it better? Okay. All right, so that is the drawings or the concept for shear, right? So now the game becomes easy. Why I'm saying that? Because now I can split my resistance between concrete and steel and design for it. Okay, so I'm just gonna open up lecture 13 and we'll continue that tomorrow, but let me just start it, right? So lecture 13, design. Okay, so from the mechanism to design. So we need to learn objective. We need to learn the design equation. Okay, design equation for shear. Okay, so what is the design equation for shear, right? So first of all, let's take a look, right? Phi Vn, that is the strength reduction factor multiplied by shear resistance, nominal. So let me name it. So this is nominal shear strength. Okay, and this is the strength reduction factor as you know it, right? And this strength reduction factor equal to 0.75. So let me write down here. So phi equal to 0.75. And this is based on ACI 2.1.2. Okay, so this is better than flexure. We don't have to compute it for it. It just give you that it's 0.75. All right. Now with this, I say that the phi Vn, which is the total shear resistance, can be divided into two parts. So that equal to phi bracket inside Vc, concrete part, and Vs, steel part. Okay, phi VC and VS, 2 parts. So usually what we do is we determine VC first, the concrete resistance first, and then we find out how much reinforcement we put in. All right, how much reinforcement we put in. And if you want to correlate to your code, and this is in ACI 22.5.1.1. Okay, so the essence of the design is to find out how much shear resistance needed from steel, and that equal to phi Vn, or actually let me say that phi Vn minus phi Vc, and divided by what is it? Phi, right? So phi got canceled essentially, right? So just that, and now Vn equal to Vu divided by phi. Okay, because don't forget Vu is applied shear, that has to be smaller or equal than phi Vn, right? Vu divided by phi minus Vc. All right, so that is the design approach. So how do we figure out how much concrete contribution we have for the concrete, right, on the section? So we go back to the equation Vc equal to Va, Vcy, and plus Vd, Dow action. And turns out that under no axial compression, this is no axial compression. So you may get confused, what is axial compression, Bob? So if you remember, when we talk about beam, right, it was supported at the end of it, and we have flexure, now we have shear. That means no axial forces. Okay, we always neglect the axial forces. Okay, we just only care about the bending moment M and the shear forces in the section. Okay, so that's the definition of no axial compression, right? So when there's no axial compression, this equation holds, and the contribution from concrete VC, okay, and I'm using 14 code definition and explain why tomorrow, why we're doing this, okay? But for now, we see the concrete contribution equal to 2 lambda square root F prime C BWD. And you can find this from ACI. You can find this from ACI 22.5.5.1. Okay, and let's take a look at this equation here. So lambda is a weight factor, right? So for normal weight concrete, okay, lambda equal to 1. For lightweight, lambda equal to 0.75. Right? It's just a weight factor. Now F prime C, we all know that that is the compressive strength of concrete. Right? Compressive strength of concrete. And then BW is the width of the web. So by definition, what is the width of web, right? If I have a rectangular beam, this is BW. Very simple. I have a T-beam, this is BW. I have an I-beam, then the middle portion of it is BW. So in another word, BW is always the narrowest distance across the section. Okay. All right. And now there's a D, and that is depth of the beam. Okay. Now this you can substitute with DS, but normally people just assume it's roughly 80% of the height for shear design. All right. So you may ask the question and say, Bob, where do we get this equation from? Is it from an analytical approach? Do we do any mathematical model, come up with this equation? The quick answer is no. We basically got them from empirical fittings, from experiments. So we've done a lot of experiments, and we got this equation, and this is really empirical. All right. Another question is, you have F prime C here, and it's under the square root of sign. So what unit we use here? We use unit of PSI. Okay, so this is the contribution by concrete. Now, how about steel? And for that, we will talk about it tomorrow in Thursday lecture. Okay. All right. I'm just going to pause here and welcome any questions. And if not, I will see you tomorrow. And if you have personal issues, please stay behind and we can have a discussion. All right.
Thank you.
Sure.
Thank you.
Yep. Okay. Let me stop recording and then let's